Okay, hey guys! Welcome to the OneClass channel. My name is Cindy and I'm currently a third-year engineering student. Today we'll be going over some commonly asked math questions at both the high school and university level. If you need any additional homework help or tutoring, please check out the links in the description below and let's get started. Okay, so our first question today is asking what is a line plot? So we have a picture here of what a line plot looks like. So it's a graphical display of data along a number line. The line plots are also called dot plots, so you might have heard it in two different ways. This is line plot or dot plot. And, oops, plot. And so in this example here, you can see that the line plot shows the distance from 20 meters to 27 meters, and it has 17 different dots spread out throughout the diagram. As you can see here, I'll just draw something similar. So we have 20 meters, 21, 22, 23, 24, I'm gonna run out of room, 25, 26, and 27, 23, 24, 25, 26, 27, ideally, evenly spaced, but they all represent the distance in meters. And as you can see, there's dots. Like I said, 17 dots, and the 17 dots represent, in this case, for this example, 17 different runners. So 3 dots above the 21 meter mark, this mark here, the 3 dots above it represents 3 runners that are located at 21, that are located at the 21 meter mark. There's 0 runners at the 20 meter mark. There's also 0 runners at the 22 meter mark because there are no dots. There are 2 runners at the 23 meter mark. I'm just referring to the diagram and how many dots we see. Above 24, there's 4 runners. Above 25, there's also 4 runners. Above 26, we have 1 runner, and above 27, we have 3 runners. Okay? And like I said, if you add all those up, we get 17 runners or dots in total. All right? Yep, so that is what a line plot or dot plot shows. Of course, this is just one example with the runners and the distance, but the number of points, you can kind of see the number of points above a mark on the line plot has that meaning. So we can go on to the next question. Say correct solution for that one. And we can move on. Okay, question 2. I mean, it doesn't really have a question, but I guess we can explain what even numbers are. So an even number can be divided by 2 without leaving a remainder. On the edge, a little bit messy, sorry. But yeah, so any even number can be divided by 2 without leaving a remainder. That just means that, or you can also say the remainder is 0. So you can also identify an even number if it ends with 0, 2, 4, 6, or 8. So if we give examples of even numbers, we can have a set that looks something like this. 0 is an even number, 2 is an even number, as we said above here. We can also have 10 that ends with 0. We can have 28 that ends with 8. 100 is an even number. 686, just throwing out random numbers here. Those are all even numbers because they can be divided by 2 without leaving a remainder or with a remainder of 0. Let's look at this example or the solution here. And so yeah, it says if a number is divided by 2 and does not have a remainder, then it is an even number. So we can easily check that the number is even or not just by looking at the last digit, which I stated, and they give some examples as well. So correct solution. We can move on to the next example. So question number 3 is asking for the formula for circumference. Okay, so the circumference is the distance of the, or I guess more properly, around the perimeter of a circle. Or, yeah, so the distance around a circle. Oh, a little bit of a wonky circle, but if we have a circle, we can measure, the radius, which is the distance from the middle of the circle out to the edge of the circle. Or we can measure the diameter, right, which is from one side of the circle to the other through the middle. And if, say, we have this perimeter around the circle, if we, I guess I could draw it, oops, like this, if we were to cut, we had, say, like a string or something, and wrapped it around into a circle. We wanted to figure out the circumference of the circle, and we cut the string and unrolled it so that it was a straight line, like this. We would be able to see that this circumference is equal to 3 and a bit times the diameter, right? So if we had, you would have 1 times the diameter, oops, too far, 2 times the diameter here, 3 times the diameter, and then this last part here, obviously not to scale, that would be 0.14, etc., with more decimals, times the diameter. So actually the circumference is equal to pi, which is 3.14159, etc., pi times the diameter. Okay, so yeah, remember, if you were to take a string or something and make it into the shape of a circle and then cut it and stretch it out, you'll be able to find that this circumference is equal to pi times the diameter. Remember, you can also work with radius. Oops, doing things with my hand here. You can also work with the radius of a circle, right? And the radius is half of the diameter, or sorry, yeah, half of the diameter, or you can say that the diameter is 2 times the radius. So we can also get that the circumference is equal to pi times 2r. I'm blocking it a little bit. There we go. Pi times 2r, and more commonly seen as 2 pi r, the circumference. So these are the two main formulas for circumference. Okay. Looking into the solution, we have this drawing of stretching out the perimeter, or the circumference of a circle so that we can measure it, and we get the same solution. Alright, solution. And we can move on to the next question. Okay, question number 4. There we go. Question number 4 is asking, what is a 30, 60, 90 triangle? Okay, so this 30, 60, and 90 represent degrees. So if we have 30, 60, and 90, we have the 30 and 60 as interior angles. Well, they're all interior angles, I guess I should say, of a triangle. And with the 90 degrees, you know that it has a right angle, or it's a right triangle, right? Because 90 degrees makes a right angle. So let's draw this triangle. Might look something like this, where we have 90 degrees in this corner, 30 degrees, and 60 degrees. Okay, so 30, 60, 90 triangle is a special type of right triangle. It has interior angles 30 degrees, 60 degrees, and 90 degrees. This type of triangle is special due to the relationship between its sides. So knowing a value of just one side will allow us to calculate the values of the other two. So let's try to work that out, okay? So if we start off with an equilateral triangle, which means a triangle with that has all the same length sides. So in this case, we're going to say x as the length of the sides, and each angle, interior angle, is 60 degrees. If we were to split this equilateral triangle, let me just label it here, equilateral triangle. If we were to split this equilateral triangle down the middle so that there is a 90-degree angle with this intersection and the bottom of the equilateral triangle, then we would be able to get our 30, 60, 90-degree angle triangle, the one that I said before, right? So let's draw it out. We have 30 degrees, 90 degrees again, and 60 degrees. Okay, and this is the other half, right? But we don't need to draw that. So we know that this side length here is x, and if we, along the bottom here, cut it right in half, then we know that this length of this side is x divided by 2. Because right, you cut it right down the middle. Now all we need to know or figure out is the length of this new side, right? So what we can do to come up with the length of this side is we can use Pythagorean theorem. So Pythagorean theorem states that if we have three sides of a triangle, we have a squared plus b squared is equal to c squared, where we can say that this is c because c always has to be opposite from the right angle, and then I think you can probably just use whichever you prefer for A and B. So I'm going to write A for this unknown side length, and then B for x over 2. Okay, so let's use Pythagorean theorem to figure out A. So let's rearrange the equation for A. So if we want to know what A is, we can say A squared is equal to C squared minus B squared, and then take the square root, and we have A is equal to the square root of C squared minus B squared. Okay, and we know what B squared, or B and C are from our triangle. So we have the square root of x squared, that's from here, minus, for B we said B is equal to x divided by 2, square that. Okay, now we can combine 2, so we have x squared minus x squared. Let's square everything inside the bracket. So we have x squared over 4, and then we can add the fractions. So if it's just x squared, we can imagine that it is 1 over 1, right? So 1, if we want to add the fraction, we can multiply it by 4, so it's 4 over 4. Sorry, that might not be clear anymore. Okay, and then 4 minus the 1 from here, we have 3 over 4 x squared. If you're unsure, you can go through that 1 minus 1/4 again. But yeah, you will get this. And then if we apply the square root, you can't take the square of 3 without getting rid of the integer. So we'll just leave it as the square root of 3. But the square root of 4 is just 2, and the square root of x squared is just x. So we get that side A is equal to square root 3 over 2x. So now we have our completed triangle from up here, right? We know what a side length A is now. So let's draw our final known triangle, okay? So if we have 30 degrees, right angle, and 60 degrees, we knew from before that this side is x. A, we now found out that A is equal to root 3 over 2x, and the bottom side, or the bottom length here, B is equal to x over 2, which we knew before as well. Alright, and this is our special triangle. So basically what that means is with this special triangle, our 30, 60, 90 triangle, we can basically be given any one of the lengths of these sides and figure out the lengths of the other sides. Okay, so let's go through an example. So if we're given the example, let me make it different this time. So if we have our 60, 30, 90 triangle, and they give us one side that is 8. Here, I'll just move down. I think this is part of the question. So here's our solved triangle. that we found with Pythagorean theorem. And here is the example. Okay, so we have B and A. Okay, so the only side that is given here is 8. But we can find out what B and A are just from the one given side. So remember, we figured out from before that B is equal to, well, they switched around the letters. Usually I would prefer because when you're using Pythagorean theorem, you need C to be the one across from the 90 degrees. So I'm going to change this to C because that's, you're going to need to use it as C anyways, and I don't want you getting confused. So we'll say that we need to find what B is. Okay, so we know that C, using our special triangle up here, we know that C is equal to X. A, well, don't get confused because now the 60 degrees and the 30 degrees are flipped from this special triangle that I have drawn up here, right? So the way that you reference the sides is the side that is across from the angle. Oh, I realize I'm talking crazy here because I labeled them wrong. So this is the 30 degrees and this is the 60 degrees as per the way I drew the triangle. Okay, now you can see that they're flipped, right? We have 60 degrees on the bottom and 30 degrees on the bottom in our example. Okay, so now we have to learn how to apply this rule I'm about to talk about. Okay, so A is going to be so A is across from the 60 degrees, and in our special triangle here in green, we see that across from the 60 degrees we have root 3 over 2. So that is how we know what side we're talking about. We're referencing it by the side that is across from the angle, okay? So A is equal to root 3 over 2, and then B, which we know is 8, this side is across from the 30 degrees, and in our special triangle, the side length that is across from 30 degrees is x over 2. Okay, so since we can't get anything with this one or this one because there's unknowns, we can figure out what x is though from our given side length, right? So if we're given that this side is equal to 8, then we have x over 2 is equal to 8. And if you multiply both sides by 2, you get x is equal to 16. Wow, okay, so now we can pretty easily find out the other sides, right? So C is equal to x. Well, we just figured out that x is equal to 16. And A is equal to root 3 over 2x. So all we have to do is take root 3 over 2 and substitute in 16. And 16 and the 2, or 16 divided by 2 is 8. So your answer for A is root 3 times 8, or you would usually write the 8 out in front just so that it's easier to see the separation there. Okay, so now we have solved the entire triangle. So I'm just going to redraw the triangle with all of our known side lengths now, so we can find or see the solution. So we have 6, oops, I'm drawing it wrong again. We have 30 degrees on the bottom, 60 degrees the top, your 90 degree angle. We just found out that C is equal to 16, A is equal to 8 root 3, and B is the given angle, which is 8. All right, and that is the final solution. So we were able to see both what the 30, 60, 90 degree angle triangle is, like how we got to it from an equilateral triangle and the Pythagorean theorem, so that we are able to find this special triangle. Label it special triangle, meaning that if we are given one of the side lengths, we are able to find the other two side lengths as we saw in this example. And that's it for this question. All right, so we get the same answers. We have angles of, the side lengths of 8 root 3, 8, and 16. So that's correct. And we can move on to the next question. Okay, question number 5. So this question is asking, what are the identity elements under the 4 fundamental operations? Okay, lots of confusing terms. So first of all, let's state what the 4 fundamental operations are. Operations. So that includes addition, subtraction, multiplication, and you probably guessed it, division. Okay, so those are the 4 fundamental operations. And what is an identity element? Identity element, that is when a number is added, subtracted, multiplied, or divided by this identity element, the number will stay the same. So basically, the identity element will not change when being applied by or applied to a number. So identity element will not change the number it's being applied to. It's a better way to say it, I think. Okay, let's look at the examples. So I'm going to go through each of the fundamental operations and talk about what is the identity element for each. So typically it's either, you'll see that it's either 0 or 1. Okay, so let's start with addition. So under addition, if we have a number or a value a and we add 0, then we get a back, right? So in this case, the identity element is 0. For subtraction, if we have a value a, and so we subtract 0, we get a back again. So in this case, the identity element is 0. Let's see, for multiplication, if we have a, and well, I mean, you want to try multiplying by 0, you know you get 0 back, right? So in this case, the identity element is not 0 anymore. In this case, it's 1. You know, a times 1, or any value times 1, you get back be the value without being changed. So A, 1 in this case is the identity element. And finally, for division, if we have our value A and we're dividing by 1, we get A back. So for division, the identity element is 1. So as you can see, for addition and subtraction, the identity oh, I hit something else again. Sorry about that. Identity element is 0, but for multiplication and division, the identity element is 1. Okay? And let's look at some examples. So let's see. So 20, if 20 is A, let's look at the addition operation. We have A plus 0 is equal to A, and we can see here that 25 plus 0 is equal to 25. If we have subtraction, applying this to any number, we have 32 minus 0 is equal to 32. For multiplication, multiply by 1, you get the same thing back. 21 times 1 is equal to 21. And finally, for division, 30 divided by 1 is 30. You apply this here. Okay? So you can see that in examples 1 and 2 with division and subtraction, identity element is 0. And for examples 3 and 4 with multiplication and division, the identity element is 1. So that solution is correct. And we can move on to the final 2 examples. Okay, question number 6. So we're asked, how do you convert minus pi radians into degrees? Okay, so we want to convert from radians into degrees. So the conversion factor is given as 1 radian is equal to 180 degrees over pi. Okay, so let's try that. So if we are given, I don't know, I guess if we're given minus pi radians and we want to convert it to degrees, then we would want to multiply this by 180 degrees over pi, I guess radians, right? You can see here that this cancels out. Actually, the pi and the radians cancel out, and we are just left with minus 180 degrees. We can also say that 180 degrees is equal to negative 180 degrees is just equal to 180 degrees. And that's because if you were to look at a straight line, which is what 180 degrees is, going around 180 degrees in this direction, positive direction, or if you were to go around in the negative direction, minus 180 degrees, you will end up at the same point, okay? So in that case, they are equal, right? Starting from 0 degrees, going from 180, they will be equal. And so therefore, we get the answer that minus pi radians is equal to 180 degrees. That's the final answer. Right. And that's what we got. So solution is correct. Correct solution. Oops. Exclamation point. And we're good to move on to the next question. So in our final question, we are asked, what are special right triangles? So let's talk about two different types of special right triangles, okay? So two types of special seeing that line, special right triangles. So remember, a right triangle means that one angle is 90 degrees. So this symbol I just drew here is a symbol that means angle. So right triangle means that one angle in the triangle is 90 degrees. So there's two types that we're going to talk about. We have the isosceles triangle. Isosceles triangle. Yep, okay. It's hard to spell. Which is the 45, 45, and 90 degree triangle. So let's draw that one first. Here we can look at it here. So this is what the triangle looks like. Alright, so where we have the 90 degrees in this corner, we have 45 degrees and 45 degrees in the other corners, and this this side length here, oh, that was the wrong color. This side length here and this side length here should be equal. They should both be x long, and this length here, opposite from the hypotenuse, will be root 2x long, okay? So as you can see here, we have two of the same, hit that again, sorry about that. We have two of the same angles, and we have two of the same side lengths. Alright? And the reason why they wrote it here without the x's for the side lengths is because you can see that if we, this was A, this was B, and this was C, we can compare the ratios of the side lengths, A to B to C, and we would see that they were 1 to 1 to root 2, okay? I think my computer is freaking out. Okay. We can read here. Side lengths create a ratio where the measurements of the hypotenuse is root 2 times the measurement of each leg. So that's the reasoning behind this. If you went through Pythagorean theorem, you would be able to find that with A and B given as x, so let's just do that quickly. We have a squared plus b squared equals c squared. And if we had this, and we wanted to find out what c squared was, we just take the square root of both sides, right? And we would be able to find that it's square root of 2x is equal to c, or that go, or that it's root 2x is equal to c. Okay, so that's how you came up with that from the ratio. And this is the ratio of side lengths. Okay, so that's the isosceles triangle. That's considered one of the special triangles. And let's look at the second type of special triangle. We have the 30, 60, and 90 degree triangle. Okay? So I explained this one previously. Let's go through it again. So what this is actually half of an equilateral triangle. Let's draw that. So if we have this 30 degrees, 90 degrees, and 60 degrees, but if we look at the full picture, the full equilateral triangle, imagine that we took this full equilateral triangle. Imagine if all these angles were 60 degrees and this full angle here was 60 degrees. If we cut that in half, we would be able to get side length where this is x, this is half of x, and this is root 3 over 2x, which can be found with the Pythagorean theorem again, which can go through quickly. And this is half of 60 as it was 60 degrees before. The half is 30 degrees. So this is the second special triangle. Let's look at what it says here. So once again, we have the ratio of side lengths. So if we look at, start with this is C, this is B, for example, or A, or you can swap A and B. And if you take the ratio of side lengths A to B to C, you would be able to find that the ratio is root 3 over 2 to 1/2 to 1. And usually ratios would like to be with whole numbers or integers and not fractions, so we'll multiply everything by 2 to get root 3 to 1 to 2. Okay? So that's the reasoning why they don't have fractions in their example. And as I said before, the way to find A can be with Pythagorean theorem. So if we start with their equilateral triangle with all 60 degrees and all side lengths of x, then we know that C is x already because we did not touch that side, and we know that B is half of x because we cut this equilateral triangle down the middle, so the remaining side length is half of x. So we can find what A is using Pythagorean theorem again. So we have a squared plus b squared equals to c squared. Rearranging for A, well, we already know, let's just put that in, what we already know. We have b squared and we have c squared already. Let's rearrange for A, so we have a squared is equal to x squared minus x over 2 squared, and let's take the square root of both sides, a squared minus x over 2 squared. If we expand that square bracket, we have x squared on top and 4 bottom, and if we add the fractions, or sorry, subtract fractions, because we can imagine this is 4 over 4. We get 3 over 4 x squared, which gives us root 3 over 2 x squared when you apply the square, oops, just x, when you apply the square root to everything underneath it. And that will give you what the side length or the ratio is for A. So yeah, all in all, this is the ratio for the 30, 60, 90 triangle, and that is our second special triangle that we'll talk about today, or that's, well, all of them, because the question was asking what are the special right triangles. All right, so that's everything for that question, and the solution is correct. And okay, so that's all we'll be covering today. If you did find this helpful, please leave a like, and if you want to be notified of when we do another Q&A like this, please hit the subscribe button and the notification bell. If you want to submit any of your own questions, you can see the links in the description below. And thank you